Next is sulfonation, right? Now here H plus is replaced by sulfonic group. In this case, I can also tell you that it is actually this which replaces. SO3 is a neutral electrophile. Okay. Sulfur trioxide is a neutral electrophile here. Let me first give you the reaction. See, when benzene is treated with, say, concentrated sulfuric acid or even fuming sulfuric acid can also be taken, right? Fuming sulfuric acid is nothing but sulfuric acid containing extra sulfur trioxide, also known as oleum, right? Now, for convenience, let us take it this way. Simple. You get benzene sulfonic acid. Okay. This is a basic reaction. Now, let us take the mechanism. The first one, as usual, is the generation of electrophile. Take 2 molecules of sulfuric acid, from which we'll be getting the, the neutral electrophile, then H3O plus, and of course HSO4 minus. So here the electrophile is SO3, a neutral one. Okay. Now the second step, formation of sigma complexes. Now this sulfur trioxide is attacked by the benzene ring. Come on, let us take it this way. As and when it attacks sulfur, the bond between sulfur and oxygen migrates towards oxygen, which is more electronegative in fact. Now this step is the rate determining step or the slow step of the reaction. Now, let us take it this way. HSO3 but a minus charge because the bond has migrated towards oxygen, gets a negative charge, right? Now this positive charge. Now this undergoes a resonance. Get this one. The mechanism is the same almost. I've already seen halogenation and nitration. See, these are the sigma complexes. One second. Now the resonance hybrid for these sigma complexes can be given as these are sigma complexes or arenium ions, but the resonance hybrid is this one. It is because right from here to here, the positive charge is moving, right? Okay. Now, let us consider the first sigma complex and form the final product. Okay. Now consider HSO4 minus. In the first step, we got sulfur trioxide, HSO4 minus, and even H3O plus also. Now this abstracts the proton. So we'll get SO3 minus, right? Along with that, of course, sulfuric acid. Now this SO3 minus with the H3O plus, nothing but H2O and H. That's it. You get benzene sulfonic acid. So this is a mechanism of sulfonation. Finally, benzene sulfonic acid is produced. Now, a very important point with regard to kinetic isotopic effect. Yes, sulfonation shows primary kinetic isotopic effect. But it's not because the carbon hydrogen bond is undergoing cleavage in the rate determining step. We have seen that. The carbon hydrogen bond is not undergoing cleavage in the rate determining step or the second step. It is undergoing cleavage in the third step. But still, it shows primary kinetic isotopic effect. It is because there is a negligible difference in the energy level of the first and second transition state of the free energy diagram what I have given, right? So this is very, very important. Negligible difference in the energy. So that is the reason why it actually follows this order. Remember, only in sulfonation we got this. We did not see this in halogenation. Even in nitration also, we have not seen this. There was no kinetic isotopic effect. Of course, even in this also, let me again tell you that the carbon hydrogen bond is not undergoing cleavage in rate determining step, but it is because of some other reason, sulfonation is showing a primary kinetic isotopic effect. We have discussed in detail about the kinetic isotopic effect in elimination reactions. Check it again. Now, the Friedel reaction. See, in Friedel reactions, the first one is alkylation. See, in Friedel alkylation, H plus is replaced by R plus. A weaker electrophile H plus is replaced by R plus. R plus is nothing but alkyl carbonium ion. A carbocation. Now see the reaction. See, when benzene is treated with the alkyl halide in the presence of a Lewis acid, again, which helps in the generation of electrophile, AlCl3 or BF3, even FeCl3, SnCl4, or even ZnCl2. These are all Lewis acids. Now, H plus gets replaced by R plus. Now the mechanism. The first step is the generation of electrophile. Let us take alkyl chloride along with a Lewis acid AlCl3. A pair of electron is given to aluminum. Then we get R plus, of course, this AlCl4 minus. Now, R plus is the electrophile here. The second step is formation of sigma complexes as usual. See, because the electrophile is R plus, a carbocation, see, here you need to be little careful. This carbocation may undergo rearrangement. To give a stable carbocation, as usual, attack. We get H and R a positive. Undergoes rearrangement. Now these are the sigma complexes. Okay. And the resonance hybrid is this. In fact, resonance hybrid is the actual structure which gives you maximum clarity. Now the last step. Formation of end product. Now treat it with the same old AlCl4 minus that is being eliminated in the first step, right? Now, Cl minus and H plus. This will give us the alkyl benzene, then HCl, of course, the Lewis acid, AlCl. So this is how we get alkyl benzene. This point is very, very important. Let me give you an important point. Now see, in this reaction, we cannot use the BCl3 as Lewis acid. I mean, for generating the electrophile. It is because when this happens, bond that is going to break, bond that is going to form, so this is going to get a positive charge and this is going to get a negative charge finally. But now let me show the partial positive and partial negative charge. See, once this bond breaks and this bond forms, you are going to get something which does not exist. BCl4 minus, it does not exist. So we don't use BCl as the Lewis acid for the generation of electrophile. Right? Now, let us now go for Friedel acylation. See, in this reaction, H plus is replaced by RCO plus, nothing but acyl carbonium ion. This is the electrophile in acylation reaction. acylium ion. You can also call it this way. Now, when benzene is treated with acid chloride in the presence of anhydrous aluminum chloride or ferric chloride, or of course any Lewis acid, H plus Cl minus. Now H plus is replaced by RCO plus. We get acyl benzene. Then H. Okay. Now the mechanism. First one is generation of electrophile, making use of the Lewis acid. Now, a pair of electron is given to the Lewis acid. RCO plus, the electrophile is generated, plus of course AlCl4 minus. Okay. Formation of sigma complex. Benzene attacks. Resonance. Then this one. Now, these are the sigma complexes. And this is the resonance hybrid. Then the last formation of end product. Plus the AlCl4 minus that we have removed in the first. That's it. A minus charge here, but that will go off when Cl minus attacks H plus. That is how we get the final product, acyl benzene. Yes. Plus, of course, HCl. So this is a mechanism of Friedel-Crafts acylation.